Okay, so where we left off last week, we finished off with module 2. We went through all the calculations sort of through questions. And we're going to leave that behind for the next 2 weeks before we come back and do it again in an exam setting. So the next 2 weeks will just be starting off module 3. We're not finishing module 3 in 2 weeks. We're essentially splitting it in half, and we're going to be doing half of module 3 in the next 2 weeks. It's a difficult module. The start isn't too bad, but it gets pretty tricky towards the middle. And we will only just start to touch on that towards the end of next week. What is module 3 about? It's basically about chemical reactions. We've talked a bit about chemical change before, so we relate back those concepts of chemical change, physical change, and then we talk about all the different reactions that can happen. So I don't know if you remember from the last session, a lot of the questions started with a reaction, and I had to give you the reaction for most of those questions. I'll give you the products. After this session, hopefully you should be able to do those equations on your own. So you would find out from this session what the products are from each reaction, and be able to identify what.
Hey, sorry I'm late.
All good, no worries. And Hugo, you all good as well? Got the notes? Okay, cool. So today we'll be talking about chemical change, all the reactions possible, hopefully, and we'll touch on metal reactivity as well. Next time, we'll kind of pick up midway and try work our way down as far down as possible, but it gets pretty rough through the middle. So all the reduction oxidation stuff, other schools like to teach it in year 12 because it's like a lot of fine details and finicky stuff. It's a bit conceptual and it just takes time to get a grip over it. So we won't focus too much on the super hard stuff. We'll get some of it done, but we're not going to do it all. We'll ideally want to get through the oxidation reduction concept as much as possible, but for now, we'll start with the reactions. Just to frame where we are in the term again, we're essentially in week 6 this week. We've got 2 weeks on module 3, and then we have the exam the week after, which does all of module 2 and just the start of module 3. And then the week after that, we go over the exam. And at that point, you should be more or less prepped for what's coming this term at school. The only thing that you wouldn't be super well prepped for is if you have a module 3 included in your exam this term. And if you do, let me know and I can arrange something to make sure we're covered with that base.
Yeah, sorry. I don't know if ours is mod 2 or 3, but it's a depth study this term. So we're doing like rate of reaction.
Okay, that'll be at the end of mod 3. So we might have to fix something up there.
Sure.
If you need to go over it. So just send me the notification and let me know when you have that exam or the depth.
Sounds good.
Sweet. Okay, so let's go. Chemical reactions. What are the products of a chemical reaction is the broad inquiry question. So we always start broad. Going back to what we've talked about, what actually makes up a chemical reaction? How can we say something is a chemical reaction?
Like if there's an irreversible change.
Irreversible change. Good idea. I would say this is a sign sometimes of a chemical reaction, but not necessarily the only thing that defines a chemical reaction. So this is like an indicator. I'd put in brackets. What else might you see in a chemical reaction? What helps us see a chemical reaction too?
We can see like maybe gas forming or like a solid, like a, what are they called? Like the insoluble, I forgot what it's called, but like.
We'll touch on it in a second, but you're right. So if you make a gas or you make a solid and you see something forming, that could be a sign of a chemical reaction again, but not always. But not always. I'll put in brackets again.
Is it like a change of color? And I think he meant like a precipitate.
Yeah, a precipitate is the solid that you form. And yes, you could have a change in color too. Again, is it definitely a chemical reaction? Might be, but it could also be a physical change.
Is it like if a new substance is formed?
That's what we're more leaning into. Did we form something new? And was there a change in composition from the start to the finish? That's the big overarching idea of what makes something a chemical reaction, is you have a change in composition. And I keep saying this, you're probably sick of it by now, being reminded. chemical change, we think change in composition, as in we start with these two molecules, we end with things that are completely different or rearranged. We start with hydrogen and oxygen, we end with water. That is a chemical change because we've started with two molecules, we ended up with a different molecule at the end.
So has it got something to do with intramolecular forces?
Yes. So it'll be a rearrangement of the intramolecular forces. Because intramolecular, we're talking which forces, Andrea?
Like inside the actual molecule, not like between them.
Yes. And what kind of bonds would be intra?
I got no idea.
Anyone else? What bonds are intramolecular?
Is it like covalent?
Yeah. Covalent. And you can also technically say ionic, but it's not really a molecular force. You still consider it intra. So change in composition, I'm liking these ideas. We have the intramolecular forces being changed. And this could be due with ionic or covalent. And for our purposes, we can also maybe consider metallic, but metallic is always a little bit more peripheral for our purposes. Okay, good. So chemical change. Big thing that I want you to take away is that chemical change implies a change in composition. And you'll be forming new substances by the end of whatever you did. This is different to a physical change because physical change, you will not have a change in composition. Oftentimes it will just be a state change. For example, you go from liquid to gas, you go from gas to liquid, liquid to solid, or you can even go from solid to gas or gas to solid. These are all physical changes because something started as a gas and it went and turned into a liquid. So our water vapor condensed into liquid. You see how the molecule has not changed over the course of the reaction. Well, it's not a reaction, it's a change. The molecule hasn't changed. In composition, it's still H2O. Therefore, you cannot possibly have had a chemical reaction. It is a physical change in this case. Does that concept make sense for everyone so far? Okay. So then relating to the next things we just talked about, there are things that can show us that we might have a chemical change going on, but it's not 100% guaranteed. So Andrea mentioned that we have the production of bubbles, potentially production of a gas is something you might see in a chemical reaction. So if you had a reaction between calcium carbonate, CaCO3, and as always, stop me if anything doesn't make sense. Please ask questions along the way. CaCO3 goes to CaCl2, which would be, and H2. So this would be balanced and we're fine. So from this chemical reaction, why have we made bubbles? It's because we made a gas. Because the chemicals that we started with have changed in composition, and the things we end up with are not only of a different composition, they're of a different state. So sometimes the products you make will be a different state, and you can see that visually with bubbles. And you can test with a lime water test. Has anyone seen lime water before? Lime water test? What happens?
Gets cloudy.
Gets cloudy in the presence of? Oh wait, sorry, I've written this equation completely wrong. Apologies. H2O and CO2 are actually the products here because it's a carbonate. So it gets cloudy in the presence of CO2. Lime water gets cloudy in the presence of CO2. And that's a test you can confirm the presence of CO2 gas. So there's different things you can observe. You can run tests or a pop test for hydrogen gas if you ever suspect that. So that's the one where you capture hydrogen gas underneath a test tube, light a match, and it goes whoop, big pop sound. Okay, so the first thing, production of bubbles. Other signs, production of an odor. So if you can smell something, you might have made a gaseous product. Change in temperature is a pretty good one. A change in temperature just from a reaction oftentimes is a pretty good sign that there's breaking and making of bonds. And I want to introduce the concept of breaking bonds, consuming energy, and making bonds releases energy. This is a concept that will stay true until the end of HSC. Breaking bonds consumes energy, making bonds releases energy. So the way I always remember it, if I had a pencil in front of me, and this is modeling a bond between two atoms, in order to break the pencil, I'd have to put in energy and snap it apart. And if I was to ever put it back together, and I put it back together at a quick speed, it'd snap together and make some sound. And that's the release of energy. That's kind of how I try to visualize the breaking and making of bonds. But try get that clear in your head that breaking bonds consumes energy and making bonds releases, because that will tell us in a reaction whether the temperature of the system will increase or decrease. Has anyone heard of the terms exothermic, endothermic? Okay. Sophia, do you want to have a go explaining in your words? What would you say exo-endo is?
Wasn't exo when it like releases energy and like endo when it like takes it in instead?
Yes, perfect. I love
Yeah.
the body language as well. So then how does that relate to the bonds? Because when we've just introduced the idea of bonds releasing and consuming energy, if we're exothermic, what must have happened to bonds? Exothermic releasing energy. Did we break more bonds or did we make more bonds?
We
Right.
made bonds.
Made more bonds, right? Made more than broke, because that would be a greater release compared to taking in of energy. And vice versa is true for an endothermic. You'd have an overall consumption of energy, which means the temperature of the surrounding is going to drop. And that's the case where you have to break more instead of making. So change in temperature often is one of your best signs if you can detect a change in temperature. Okay. Formation of a precipitate. Again, usually a pretty good sign, one of the stronger ones. So a precipitate, to define it, is an insoluble solid formed when you mix two solutions together that contain ions. And today we'll cover when you will and won't make these precipitates. It's to do with solubility. We'll talk on it some more. But as an example, if you combine silver nitrate, AgNO3, with NaCl, you would form AgCl solid and NaNO3 in solution. And so when you combine them together, your solution actually turns a white color. And this is the presence of your AgCl precipitating. Despite both solutions starting clear, you combine them together, you end up getting a cloudy white solution, which is the presence of this solid AgCl floating around. So another sign of chemical change. We had change in composition from start to finish. AgNO3 is no longer AgNO3, it's now AgCl. And NaCl is no longer NaCl, it's now NaNO3. Chemical change. Change in color, slightly weaker one, but in the right context, very clear as well. So if two clear solutions suddenly turn blue, or you mix a pink and a blue and it turns like completely unrelated color, that's a good sign it's a changing color, but be wary with changing color that you're not just mixing two colored solutions and reaching a middle ground. So if you mix a blue solution with a yellow solution and you make a green one, that's not necessarily a changing color indicating a reaction. That's just mixing two colors together, like paint. If you mix green paint and orange paint, you're going to make, well, I picked two bad colors. Brown. Lots of colors there. So brown, and just be wary that when you're changing color, be sure it's an unrelated color, not a middle ground. And the last thing that Hugo mentioned too is that reactions tend to be difficult to reverse. So if you complete a reaction, it should be difficult to go back. It shouldn't be so simple as you can just decrease the temperature and it goes back to what it starts as. This is in contrast to a physical change like melting ice and freezing water. State changes are very easy to reverse just depending on how much energy you input or take away. So to summarize everything we sort of talked about there, we had a few indicators of chemical change, but in chemical reactions, you have a rearrangement of bonds, and that's in accordance with the law of conservation of mass What do we say that was last module? Law of conservation of mass.
That new bonds can't be created or destroyed.
New bonds can't be created or destroyed. The created or destroyed part is what we want, but we're not so much talking about the bonds, because you can break and change bonds between
Oh, sorry, the mass.
the mass, and we would usually say matter as well.
Okay.
So when we say law of conservation of mass, it's very closely related to law of conservation of matter. And so we can change matter from one form to another, never create or destroy matter. Okay. So in the context of what we just talked about here with a chemical reaction, you can start with something and you end with something, but the things you started with, all the atoms, have to sum up to all the atoms you finish with. That's the big idea in a chemical reaction. That's why we need to balance our equations. Otherwise, we violate this law. And we can never, ever, ever violate. Never possible. So if you're ever asking yourself that question, did I violate the law of conservation of mass? The answer is automatically no, and you'd figure out why is your equation wrong. All right. And finally, because you've rearranged bonds, you've kept the same matter, but rearranged it in a different form. So you have the same number of atoms with different reactants, different products. You have to have made new substances in your chemical reaction. So let's see how that can take place in a few different scenarios. Just one dot point to get through before we get into the actual reactions. Modeling chemical reactions, they kind of just want you to understand what a scientific model is. So the dot point reads, modeling, use it to demonstrate the rearrangement of atoms to form new substances and also the conservation of atoms in a chemical reaction. Just to be clear on what a scientific model is, it's absolutely anything you want. So it could be an idea, it can be a tangible object. The only purpose of a scientific model is to make things easier to understand. So they simplify the phenomena into simpler concepts, just like before I was trying to explain to you with a bond, how exothermic and endothermic works. I was modeling a bond with my Apple Pencil, and it helped you guys to understand the concept of a bond through the concept of breaking a pencil and putting together a pencil. Obviously, this is not a bond, it's much bigger. I didn't actually release any energy or take in any energy, so there's inherent weaknesses to my model. But would you say it made it a little bit more easy to visualize and understand what was going on? So that's the idea of a model. It makes things easier, and no model is perfect. Every model has weaknesses. This is what your teachers love you to dig into. So when this dot point comes up about modeling, oftentimes what they want is for you to actually critique models and tell them what's bad, not just say that this model is doing this, great, thumbs up. You should be saying this model sucks because, and then rant. Okay, but the specific model they like to focus on for this dot point is molecular modeling kits. I'm sure you've all seen it through junior science, the balls and sticks. So elements as the balls, bonds represented by the sticks, helps us to model a chemical reaction. So looking at this model, can everyone write the chemical equation that's shown by the diagram? So the black balls are carbon, the white balls are hydrogen, and the red ones are oxygen. Either write on paper or in the chat, I don't really mind. It's a bit longer, so maybe just write on paper. And no need for states for the time being. Okay. So we should have gotten something close to CH4 plus, the red is oxygen, O2, which goes and forms CO2 and water. Does anyone know what type of reaction this is for bonus points? It's okay if you don't yet. We're about to cover it.
Is it combustion?
It is combustion. Well done. So combustion, any reaction with oxygen, burning in oxygen is combustion. So using plastic balls and plastic sticks, we were able to represent what happens in a combustion reaction. That's the idea of a model. It makes things easier to understand, but it has weaknesses.
Wait, sorry, wouldn't the diagram show like maybe it's balanced? Because
Oh yeah, there should
you
be
go.
numbers.
Mm.
Correct. Thank you. And then for the second part, how would you say the law of conservation of mass is obeyed in the diagram? How do we say that? How is it obeyed? Yes, Sophia.
Because like we have like the same amount of like everything in one side. Like that's why you balance it, because like you have like the same amount like in the other side. Like for example, like we'll have like four hydrogens in like the left side, and we'll still have like four hydrogens in the right side.
Perfect. So
Yeah.
to summarize, we have the same number of atoms in the reactants as in the products. Same number of hydrogens, same number of oxygen, same number of carbons. So therefore, mass has been conserved and we've obeyed the law of conservation of mass. Good. And then everyone have a go. Now you can construct your own model. Draw a small model to show the reaction between oxygen and hydrogen to form water. So draw it as if it was one of these models. Okay. So something along these lines, where you're showing that you have one oxygen, two hydrogens, and two waters. I've just gone and used the same color scheme as before. For your internals, it's fine to use colors, but going longer term thinking into the HSC, they scan everything up in grayscale. So just keep in mind long-term color is not a great way to code. So if I was to do this in the HSC, for example, I would be doing these as shapes instead of colors, just to be super clear to my marker. And if you want to be really clear, you can do both shapes and colors.
Can we do like the letters as well, like the symbols, like or
Yeah.
like do
I
that?
mean, it just depends what the question asks of you, because that'd be correct as well. And you can
Okay.
include the letters inside the balls. Is that what you mean?
Yeah, or like for sorry, if we do a shape, do we just like do like a little key on the side?
Yeah, exactly. You just go like square equals oxygen
Okay.
and triangle equals hydrogen.
Okay, got it. Thank you.
All good. Okay. So looking at another more complex equation, if we counted up everything here, we see we have 7 red on the left, 7 red on the right, 2 black on the left, 2 black on the right, 6 white, 6 white. We have conservation of mass. So what this kit has allowed us to do, it's allowed us to show the rearrangement of atoms to form new substances and also demonstrate the conservation of atoms in a chemical reaction. That's what the dot point wanted. Okay, but this is where the marks really lie from differentiating the average to good to the really, really good students. You're looking at the disadvantages in this model. So the advantages are obviously what this does. It gives us a visual representation of bond forming and breaking, shows us different types of bonds. We can show a double and triple bond, and we can see the law of conservation of mass, which is great. But there's significant weaknesses in this model. You can't see the strengths of bonds, so just each bond breaks the same. That's not true. Depending on electronegativity, bonds will have different strength. It doesn't convey any information about energy changes in the bonding. Just like my breaking of a pencil didn't actually release energy. When you break apart these balls and sticks, you're not releasing any energy, you're not taking in any energy. So it's not accurately showing, is this exothermic or endothermic? Doesn't show electrons at all. So you can't see distribution of electrons across a bond. You can't see any ionic reagents forming. And the geometry is fixed based on where the holes are on the balls. So you can't make a slight distortion, for example, if there's changes in the electron placements. These are fine details. I would say pick the 3 that makes most sense to you and just run with those in your exam. You're probably not going to be asked for more than 3. But the idea is that for any model, the whole critical skills, critical analysis in year 11 that I really, really hone in on is your ability to analyze and critically appraise different things throughout science. Okay. So hopefully we've all had a go at writing chemical equations a fair bit now, know the basics of balancing. And this is pretty much our 3rd time coming back to balancing equations. So I won't really go into it too much. Are there any questions with balancing? Just the main thing, if things appear twice on one side, you always leave those to the end. That's about the only thing that I'd say I'd want to remind you guys about. But we introduced 2 new styles of equations. So up until now, we've been showing all of the species in terms of equation like the one in the example, where everything is shown bonded together and you show the states. We call this a neutral species equation. And this is what we've been using up until this point. And that's your default, your neutral species. Is if your question asks you to write a balanced equation, you write the neutral species. There's 2 other types. Now that we're going to be talking about ionic compounds a bit more, there are ionic equations, so complete ionic equations, and net ionic equations. These are slightly different. So for a complete ionic equation, firstly, this shows all aqueous substances as ions. What's an ion?
It's like when an atom has lost or gained electrons.
Good. So then if it lost or gained electrons, what must it now have?
A charge.
Charge. And so ions are therefore charged particles. Charged particles, but yeah, charged particle, leave it at that. Generally speaking, an ion is a charged particle. And whenever you have an ion, or whenever you have an ionic substance, rather, that is aqueous in solution, in a complete ionic equation, you show it as its ions. So what I mean by that is if you look at the first equation given here, the complete ionic equation, you'll see that the KBr, the potassium bromide that was aqueous, this is now shown as K plus and Br minus. K plus and Br minus. And the question is why? It's important to understand why before we actually just learn this and go with it. When you dissolve anything solution, so when you dissolve your NaCl, for example, in solution, put it into a beaker of water. Does the NaCl just sit as 2 bits of NaCl all together, a lattice of NaCl in the liquid, or is it something else? What actually happens to the NaCl once it goes in the water?
Dissolves.
It dissolves. And does it dissolve as an Na plus a Cl floating around?
No,
Lattice. What does it do?
like becomes sodium and chlorine ions.
Good. So whenever you put an ionic substance and dissolve it in water, it is going to break into its 2 ions. Whenever you dissolve something, it will turn into ions. And that's important to understand for our aqueous substance going forward, because aqueous is something that's really gray for the first half of year 12. year 11. We don't talk much about aqueous. We just say it's when you've dissolved something. But now, can we add on to that understanding of aqueous meaning dissolved? When you have an aqueous ionic substance, it means it exists as ions in solution. So that means whenever you write an equation like the one we have in black, KBr aqueous, AgCH, there shouldn't be H's here, AgCH3COO, these are ionic compounds, metal and non-metal, and they're aqueous, meaning they're going to be existing as ions. Is everyone familiar with CH3 COO minus? Someone shout out the name. What's this? Going back to the polyatomic ions. I said these become important back in module 1.
Acetate.
Acetate. Has everyone seen the polyatomic ions before? Does anyone need a quick refresher? Polyatomic ions.
Yeah, we only got told like in class to memorize like the really like the 5 easy ones, like carbonate, chlorite, and all that kind of stuff.
Okay. So how about we go through, everyone type in chat, the polyatomic ions you know. Can be any of them. Let's build up a list and see if we can hit them all.
Sure.
So I want the name and I want the molecular formula with the charge. Or not molecular, name and formula with charge.
I don't know how to like type it on the chat. Like, do it like how do you like do the like the little symbols? Like type
Like minus and plus.
like, but you know how it's like the charge plus like the little number, the bottom and stuff. Like I don't know.
Don't worry about the subscript. That's
matter?
fine.
Yeah,
Yeah, don't worry about it. As long as you know where it's meant to be. Good. And you can help each other out. Anyone know the charge on ammonia? Okay, Andrea's put in the charge for NH4+, but that's not nitrate. That's not nitrate. We've got sulfate, carbonate, ammonium, good. Sulfite as well, NO3-. Okay, we're getting a few together. So the core ones that you really, really just need to know are carbonate, CO3 2-, sulfate, SO4 2-. I'll put nitrate above with its 1-. And then on top of nitrate, I'll also put CH3COO-. This is what we call acetate or ethanoate. Both are correct. Then from what you guys have got as well, we've got phosphate with no charge. So we'll go phosphate down the bottom, PO4, and it's a 3-. It's the only 3- substance we have, or polyatomic ion we have. Phosphate, and then we had NH4 plus ammonium. Any others that are core? Okay, I think that's all the core ones for now. If any more come up, I'll mention it. Oh, hydroxide is a good one. OH-. I'll slot it in the minuses. Hydroxide. Okay, I think these are most of the main ones. And then we've got some other ones that end in ite. So Samara said sulfite, and Sophia's written out nitrite. Oh no, that's nitrate, never mind. Samara has written out sulfite. So whenever you have one of the core polyatomic ions with one less oxygen, so it's any of nitrate, carbonate, sulfate, phosphate. If it has one less oxygen, we change the suffix to ite. So this is sulfite. And for nitrate, NO2- is nitrite. I don't think you really see that form with carbonate because it just be carbon dioxide, and then phosphite you might see as well, but they're rarer. So they're kind of in brackets. The 7 above should be committed to memory as soon as possible because they will haunt you if you don't. Okay. So then going back to the complete ionic equation, before I move to that, any questions on the ions? Okay. So back to the equations, we'll talk about the complete ionic. Whenever you have an aqueous ionic compound, it will break into ions. So that happens the same for the product potassium acetate. But you'll notice for the final product, AgBr, it's a solid. So solids will not turn into ions. They'll exist in instead an ionic lattice, as we discussed back in module 1. Ionic compounds, when they're solids, they exist in a lattice. And so we don't need to turn that into ions. So therefore, our complete ionic equation is all of the aqueous ionic compounds broken into ions, still listed as aqueous, and the solids would stay as just solid. Does that
Hey,
make
wait,
sense?
sorry. How do you like tell like in an exam if they just don't give you the states, like whether something's aqueous or not?
Good question. So we'll figure that out through the reactions we do today, hopefully. The next equation, net ionic, is slightly different but the same. You do the same steps to go from a neutral species equation to a complete ionic. The only extra step to go from complete ionic to net ionic is we cut out all of the substances which exist on both sides of the equation. So Ag and Br remain. The reason why we do this is because anything that exists at the start and the end unchanged has that undergone a chemical change? No. So when we consider chemical reactions, it's always useful to only really consider what actually changed in composition. So when we write a net ionic, that's what we show. We're only showing chemically changed substances. And that's where we cut out all the things that don't change, and we call those ions that don't change, we call those spectator ions. And we cut out the spectator ions to leave us just with the net ionic equation, which is only the substances which actually participated in the chemical change, chemical reaction. Okay.
Wait, so I just had a question.
Yeah.
How come we got rid of the K, the potassium from, because didn't that change with bonding to CH3COO?
Yes. So it changed to bonding with CH3COO if it was a solid. But the way that these things exist in solution, they're just ions. So they'd be floating around, but they're technically more likely to form with an acetate. But when they exist as aqueous substances, they're just ions individually anyway. So going from one ion to another, it wouldn't be any change.
Okay.
Okay, let's have a go. Question 1. Everyone have a go at the complete ionic and net ionic, and include states. Yeah. So this is what I've come up with at the end of it. For the complete ionic, we're breaking everything that is aqueous apart into its ions. So we've broken magnesium and sulfate, barium and nitrate, and then in the products, magnesium and nitrate, but we leave barium sulfate as a solid because that will not exist as ions. Then for the net ionic, you just cut out the things that exist on both sides of the equation unchanged because they didn't undergo chemical change, and we just want to show the ions that participated in the chemical reaction and the product that they formed, which leaves barium 2+ aqueous plus sulfate aqueous going to barium sulfate solid. And just with the ordering, it is convention that you try to order the reactants in the same order they come in the products. But you wouldn't lose marks if you did the other way. Any questions? Complete ionic, net ionic? Okay. So I want to spend most of the time here. Reaction types. There's 6 reaction types that I want to go through today. So we're gonna have to move a bit quickly, but the main idea is that each reaction type encompasses a range of reactions, and the types of reactions within them, you'll have to remember the reactants that you use and the products that you'll usually form from that reaction. And you'll kind of get more of a feel of what I mean once we start to go into it. So the reactions we can learn about are synthesis, decomposition, combustion, precipitation, acid-base reactions, and acid-carbonate reactions. Out of the things that are really, really high yield, it's probably these last 4 that are specific. They're specific reactions that you just have to know. The first 2 are kind of a bit more wishy-washy. They're more general. They describe a broad range of reactions. So they're not specific reactions, but the last 4 are. Okay, so synthesis. As the name suggests, you are synthesizing something, so you are making something from smaller pieces. In a synthesis reaction, you are taking more than one part and putting it together into less than the number of parts you started with. And it's usually 2 parts going to 1 in a basic synthesis reaction. Oftentimes what you'll see is it's going to be 2 nonmetals combining together to make a covalent compound. And we saw this in the model before, where we combine together hydrogen and oxygen to make water. 2 nonmetals combined and made a covalent compound. This is a synthesis reaction. Second case, we can have a metal and a nonmetal combining to make a ionic compound. And this could be seen in a magnesium reaction with oxygen, which forms magnesium oxide. And again, this is a synthesis reaction. The last case is a bit strange. Formation of calcium hydroxide, or the reaction of calcium hydroxide with water to make calcium hydroxide. So this isn't a direct synthesis in the way we saw with the ones before, but because you're combining 2 things into one, it's still a synthesis, and this is just what we call, a bit more specifically, an indirect synthesis. Still a synthesis. So the bottom line, if you're going 2 things into one, it's a synthesis reaction. This doesn't describe a specific reaction. And then just as an example, if you did form calcium hydroxide, how would you know that you've proceeded this reaction? We go back to the indicators that we talked about before. If there's an increase in temperature, this reaction is shown because it's an exothermic reaction. Does that mean we have more bonds or more bonds broken or more bonds formed if it's exothermic? Thumbs up for formed, thumbs down for broken. Thumbs up for formed, thumbs down for broken. Do we have more bonds broken or formed? Thumbs up formed, thumbs down broken. Okay, so we would have more formed. Forming bonds, remember, snapping the pencil together is going to release some sound energy. So forming bonds releases energy. Exothermic reaction would be a greater release than consumption, and so you would have formed more bonds than broken apart. Second sign, you might see bubbles, but in this reaction, do we expect to see bubbles? We shouldn't. If it was just these things, because all we have is the formation of an aqueous salt. So when we see bubbles in this reaction, it's not because of the reaction, it's because we have actually caused some of the water to boil. That may happen as well because of the heat we released. So always being careful that indicators are not necessarily 100% true indicators of chemical change. And the last one just shows that calcium hydroxide is a basic solution. We don't really need to know that for now. Okay. So let's have a go at some of these. So hopefully having a quick read through these 6 reactions, you can see you're reacting A with B and you form C. So it's always a synthesis in these 6. Let's just go and do, let's just do B. Everyone write out B. Formation of ammonia. Oh, what's ammonia? Anyone know what ammonia is?
Is that NH3?
NH3. Good. Closely related to ammonium. Don't get them confused. Ammonium has a positive charge and has 4 hydrogens. Okay. All right. So after we've written that out, nitrogen gas, hydrogen gas, remembering that those are diatomic molecules. What's the rule to remember our diatomic molecules? What are diatomic molecules? There's 2 different rules you could have remembered. There's genene. If it ends in gen or ends in ene, it'll exist as diatomic molecules. So nitrogen, hydrogen, or for the enes, chlorine, bromine, fluorine, iodine, they all exist as diatomic, meaning they have 2. Okay, so then in this reaction, we have N2 with H2, balance the N's, balance the H's, we'll have N2, 3H2 goes to 2NH3. Are there any questions there? Okay, cool. So for synthesis, that's pretty much it. A general description of when we combine 2 things together to make one thing in the end. Decomposition is simply the opposite. You're starting with one molecule, one compound, and it will form more than one in the end. Okay, and as the first dot point says, because chemical bonds are broken, a decomposition reaction requires the addition of energy to begin. So typically, and this is actually true for pretty much any reaction, in order to start a reaction, you have to first input energy to break bonds. You can never just go about forming bonds first. There has to be an input of energy first, which breaks apart all the bonds. Molecules then reform, releasing back out energy. And based on the difference, that's how you calculate, is it exothermic or endothermic? It's about that process of breaking bonds, energy input, then the bonds reform in a new arrangement, energy output, and that balance decides, is it exo or endo? But for decomposition, there's three sources of energy that we typically see, and it's heat, light, or electricity. And each of these fuels a different reaction. There's thermal decomposition, light decomposition, and electrolysis. Once again, these are not specific cases that I would say are essential to know. Just remember broadly, decomposition is breaking of one into more than one. But just to run through the reactions, and these are reactions you'll probably never see after module 2 again. So don't spend your time memorizing these. If you see them at school, memorize them, but otherwise these are just for example. Metal oxide will break into a metal and oxygen gas if you apply heat. Metal carbonate breaks into metal oxide and carbon dioxide, and metal hydroxide breaks into metal oxide and water vapor if you put heat on it. Light decomposition, again, many examples, but the one that I've just included is if you have a silver halide. Halide being what? What's a halide? Halide. Think periodic table. What sounds like halide?
Like a halogen.
Like a halogen. And what group number is a halogen? Open to the floor. Or where do you locate it on the periodic table?
Is it 7?
7. So 7, or sometimes you see 17 if you include the transition metals, but for our purposes, it's usually 7. So it's not the furthest right row, not the furthest right group, it's the second furthest right group. So all your halogens are your chlorine, iodine, bromine, all your enes going down. And so silver halide is referring to like silver chloride or silver bromide. Okay, so when you expose a silver halide to UV light, a silver solid is formed. You'll see a decomposition where the halogen is essentially separated from that silver, even though they were once together. And then finally, electrolysis. If you put electric current through certain substances, they will break apart as well. So we'll talk a lot more on this. This is getting into the weeds of galvanic cells. We'll talk on this more later. But here we have lead bromide being broken into lead and bromine gas. So once again, decomposition. Any questions, synthesis or decomposition? Okay. So this is where it starts becoming high yield. This is stuff you do need to remember. So I'm flagging it here. The last 10 minutes, you can sort of just understand and be able to identify this stuff you do need to remember. This will be essential to starting off basically all of your mod 2 questions from here on. So for combustion, we can define it simply as burning a substance in oxygen. Burning a substance in oxygen, and the oxygen part is the highest yield thing there to remember. Because every single combustion, if you get told that you're doing combustion of anything, you are reacting with oxygen. So it's telling you the reactant. Combustion means oxygen as a reactant. On top of this, combustion is an extremely exothermic process. So when you think combustion, you're thinking inside your car engine, you're thinking burning like a barbecue, the gas that comes out of your LPG, the gas canister, that's going to be combustion. So combustion is always releasing heat. So if we're always releasing heat from this reaction, have we made more bonds or broken more bonds?
Made.
Made. right? Just get that really, really clear, because this exo-endo will come up in the next module as well. Bit of foreshadowing. Combustion metals, a metal plus an oxygen will make a metal oxide. The word equations are where you should start with learning these, and then you can apply them in different cases. So metal plus oxygen will make a metal oxide. Magnesium solid, when combusted, will react with oxygen and form magnesium oxide. So then if I told you, can you write the equation for the combustion of calcium? You should be able to do that now. Can everyone type in chat? What's the reaction? What's the equation for the reaction where you combust calcium? Okay. So combustion of calcium, we're thinking reaction with oxygen. So it's going to be calcium reacting with oxygen. We know oxygen is diatomic because it ends in gen, oxygen. And the product is going to be a metal oxide because it's a metal plus oxygen goes to metal oxide. So the metal oxide that we form will be formed from calcium and oxygen, valencies of which are 2 plus and 2 minus. And so if we swap those around, we should end up having CaO is our solid. And then balancing the numbers, we have too many oxygens, so we put a 2. And we have now too many calciums on the right, so we put a 2. And I would get this in the end with the states. So for this particular reaction, the oxide you're going to get is going to be solid. That's something you remember from now on. When you combust a metal, the oxide that you get is going to be solid. The metal you start with is solid. The oxygen is going to be gas. You now know the states. It's formulaic in the way you go from now. Whenever you hear combustion of metal, metal plus oxygen makes metal oxide, and you figure this out on the spot. Does that make sense for everyone? So that's the approach we're going to start taking. We learn each of these word equations, and you can apply it to different situations. So the next equations are combustion of organic substances. Organic chemistry is module 7. So you're not going to hear much of this again after module 2 until then. But organic substances, to make it really simple, are things that contain both carbon and hydrogen, and even simpler still are substances that contain just carbon. So if a substance contains carbon, it's considered organic. When you combust organic substances, it's a little bit different in the products you form, but the reactants are exactly the same. So they'll tell you that you combust, for example, ethene, and they'll tell you that, okay, ethene and it's C2H4. They will give you the formula of the organic substance if they want you to combust it. However, there's 2 types of combustion for organic substances. There's complete and incomplete. Has anyone heard of these before? Okay. So any of the nodders, what's the difference between complete and incomplete in your words? You go.
I think it's to do with like the products, like I can't really remember, but
Yeah.
yeah, like is there like it was one with like XX oxygen, one with like not enough or something.
Yes. So there's complete combustion being the case where you combust a hydrocarbon with sufficient oxygen supply. So there's an excess amount of oxygen present, and you don't worry about whether oxygen is going to be a limiting reagent or not. We now know what that means from last module. For an incomplete combustion, this is the case where you don't have enough oxygen and the reaction gets limited by the oxygen, and so the products actually change to adjust for this, to consume less oxygen. So we'll go through each case. Complete combustion first. When you have excess oxygen, the products will be water and carbon dioxide for complete combustion. So when you hear there's complete combustion of this, you are combusting this substance in excess oxygen. That's telling you this is the case where you make water and CO2. Water and CO2. The other case is incomplete combustion, where you don't have enough oxygen and you form water still, and either carbon monoxide or carbon solid. And we call carbon solid soot. Also the same thing that you see in the mines. When the miners come out of the mine, they got black all over their hands. That's soot. And on the insides of the big like industrial gas chimneys, the insides are smeared in black. That's also soot from the incomplete combustion that's happening in those columns. So then looking at the equations for complete, we can see that C2H4 reacts with O2, you get CO2 and H2O, and you get carbon solid and water in the bottom case.
How do we know if it's either like carbon monoxide or carbon solid? Like
Great question. And the answer is they'll tell you. So they cannot possibly give you an incomplete combustion without telling you which of those two you form. So the questions will read something like this below. These are the three cases you'll basically see. Complete combustion of this, incomplete combustion of this forming this, and incomplete combustion of this forming soot. So it's like there's three cases. It's always the same. Always the same. So let's
No,
have a go.
I
Yep.
mean, for like the incomplete, like you know how it's either carbon monoxide and like carbon solid, I think. That's what like how do we know which one of the two for like
Yes.
these?
So it'll only be one or the other in the for the
Oh, okay, sorry, I reread it. Never mind.
okay, all good.
Okay.
But just to be super clear, it'll be one or the other for the purposes of when you're writing equations. But in reality, just to confuse you more, there will be a mix of both in reality. For our purposes, when we write equations, they'll tell you only make one. And just to make it really clear how to remember these, for complete combustion, we say we have lots of O2, right? Lots of O2 compared to little O2. You can see that the carbon-containing molecule you form will decrease in oxygen content as you minimize the oxygen that you have in the system. So if you have lots of oxygen, you're going to make CO2, a little bit less, and to the point where oxygen is now limiting, you're going to make carbon monoxide. That's going to be a unclean burn. And then, I don't know, it only becomes not clean once you start forming soot, where you really reduce the oxygen and you're limiting the supply. And you'd have a flame that doesn't burn blue, it burns like a charred color, you get smoke forming. That's when you can tell you're making soot and you're limiting the oxygen supply in your burn. Okay, but these are questions from module 7. So if you can do this already, you're up to scratch with year 12. Can we write the complete combustion of pentane, number 1? And can we write the incomplete combustion of butanol forming soot? Just do it on the paper. It'll probably take a little bit longer otherwise.
Do we balance as well?
Yes, please. And when you've balanced, just give me a thumbs up, either with a reaction or your physical thumb.
What's the easiest way to balance like when for the second one? Because it's like really, really complicated.
Yep. So the first thing that I would do is figure out things that appear twice on any side and leave those to the end. So looking at that, what are you leaving to the end?
Wait, appear on both sides, like in the same one.
Yeah, as in it appears on the one side.
Oh, yes, yeah, oxygen, yeah.
Yeah, oxygen will leave to the end. So if you balance everything else, you get to a stage where either it works itself out or you need to use a decimal. Is that where you've gotten to?
Yeah.
So then you can use a decimal. That's
Okay.
kind of the lifeline you can throw in these questions. You can either use a decimal, or if you don't want to go into decimals, you can just double everything and then it should work. So there are two workarounds you can use. I'll just give another 10 or so seconds. All right. Cool. So out of 5, can I get a confidence factor on those balances? 5 being very confident, 1 being quite unstable. Okay, cool. So for number 1, Samara, I'm not sure, couldn't see your number, but did you get an answer for number 1?
Yeah, I did.
What numbers do you have?
I got 0 for the first one, 8, 5, 6.
8, 5, 6. And then just with the first one, we wouldn't say 0, we'd say it's technically 1, but like, I know what you mean.
Yeah.
C5H12, let's see, 5 carbons, checks out. 12, 12, and 16. Good. This is correct. Any questions on 1? And number 3, Sophia, do you want to take us through?
I did, do you want me to like tell you all of them, or like do you have to say the number?
I guess just say the number and then whatever it was behind it.
For the first like one, like 1, and then 2 O2, and then 4 C solid, and then plus 5 H2O.
5 H2O. So then we have 4 carbons, 10 hydrogens, and 5 oxygens. Checks out for me as well. So 1, not 1,
Yeah.
2, 4, 5. And that works for me as well. Cool. Any questions? Great. So you have your technically 4 cases of combustion. Memorize these. These will be very useful going forward. Displacement reactions. Okay. So this is where I got with the other class. I think it's my problem with putting too much into the session overall, but we'll see how far we can get. Displacement is where you take 2 two ionic compound, or you take an ionic compound and react it with something else, whether it's a metal or another ionic compound, and you are essentially swapping out one part with another, probably best seen in A plus BC goes to AC, and there should be a plus B on the end. So essentially all you've done is you've swapped the A with the B, and hence you've displaced the B from the ionic compound. So in an actual equation, zinc plus copper sulfate will react and form zinc sulfate and copper solid. Zinc has displaced the copper, so that zinc is now inside the molecule, or inside the ionic compound form, should I say, and copper solid has been displaced. Okay. The other case underneath is what we call a double displacement. A double displacement, AB plus CD goes to AD plus CB. And you can see that essentially all that's happened is the B and the D have swapped places. And we'll talk about that just after this. But for displacement reaction, you're putting a solid into solution. That solid is reacting with the ions in the solution, and a different solid is coming out. That's kind of the macro understanding you need to get. A solid goes in, reacts with the ions present, and a entirely different solid comes out. And the way that you can tell whether or not something will displace something else is using what we call the reactivity series. So if you have your formula sheet with you, you can find this on there. Otherwise, have a look for it later. But this is on your formula sheet. So it says some standard potentials, and it lists all of these different ions and these voltages going down. All that I want you to take away from today is for the positively charged ions. The closer to the top it is, the more reactive, and the closer to the bottom it is, the less reactive. Closer to the top, more reactive, closer to the bottom, less reactive, and this is for all of our cat ions, our positively charged ions, positive cat ions. So why is this important? It's because when you introduce something like zinc into copper sulfate, zinc will only displace copper if it is more reactive. So the solid you introduce will only displace if it is more reactive than what's already in that solution. So we can look at our reactivity series and we see that zinc 2+ lies well above copper 2+ in the series. Hence it is more reactive, copper 2+ is less reactive. Zinc will want to displace copper, and copper is removed as a solid. It's basically the way you need to understand it. If it's more reactive, it will displace. So then going to the next one, what will happen if you put magnesium in solution with hydrochloric acid? Will it displace or will it not? Thumbs up, thumbs down once you get an answer. Will magnesium displace whatever's in hydrochloric acid? Thumbs ups. Thumbs up. I would say it would, because we're comparing magnesium against whatever the cation is in hydrochloric acid, which is going to be the H+. So we find H+, and you can see that magnesium is more reactive than H+. Hence, it will displace the hydrogen. Okay. So then let's throw a curveball. Okay. How about how about PB lead going into Fe Cl2? Displace or not displace? PB into FeCl2, does it displace or does it not displace? Okay, so the answer is no. And can anyone explain to me why I picked iron? Why is iron a good one to pick? To make it a bit trickier.
Is it because it's a transition metal?
It is. And so why might that matter on our standard potentials?
Maybe because the like it doesn't have a distinct charge. Because
It doesn't have a distinct charge. It has distinct charges.
but not it's not the same, yeah.
Yeah, so there's actually two entries for iron. There's iron 2 plus and there's iron 3 plus. And depending on whether it was 2 plus or 3 plus, you could have read this differently. But you can find out the valency by looking at the ionic compound. You can tell that this is going to be iron 2 chloride. And hence it's the Fe2 plus version. And our lead lies underneath and is less reactive. So just be wary on this reactivity series. Whenever you have transition metals you're dealing with, the ones that you want to be wary of are iron, you want to be wary of copper, although the disparity is not so big in copper. Iron's the big one. Whenever you see a transition metal, just perk your ears up and have a good look. Okay.
I was gonna ask a quick question about the double displacement.
Yes.
Like what is produced, like how do you know which one's like aqueous and which one's solid for like the double displacement?
Great question. And that leads on to the next
Oh,
part.
okay.
Precipitation reactions, and these are your double displacements. So you're clearly on the ball. We've got precipitation reactions, which are essentially double displacements. And there's a set of rules which guides whether we'll precipitate or not. And the rules are called the solubility rules, creatively named. So the rules tell you yes or no, will something dissolve or not. But before we get into that, we have to define what solubility is. So when you think of the word soluble, we think of something that can go into solution and kind of vanish. That's sort of how we perceive it. If you put salt in pasta water, that's the way you've always seen like solubility, dissolution. So something that's soluble, we have a threshold for what is soluble. If you can dissolve 10 grams per liter, it's soluble. Slightly soluble if it's 1 to 10 grams per liter, and insoluble if it's 1 gram per liter or less. So substances that are considered insoluble would be the ones that tend to precipitate. And often the ones that do precipitate very readily are the ones that are way less than 1 gram per liter. Way, way less. So when we do a precipitation reaction, you're combining two solutions of ions, AB aqueous plus CD aqueous, and in a double displacement, the two cations will swap place, or the two anions will swap place. It has to be the same thing, because you'd end up with a positive with a negative and a positive with a negative. You can't end up with a positive and a positive and a negative and a negative. So it's always a metal and a non-metal in this context. And sometimes you'll form precipitate, and usually it'll be one precipitate, one soluble salt. It's not very likely that you're going to get two precipitates, although I'm pretty sure it is possible. Very, very rare. And sometimes you might not even get a reaction. Okay. So the rules are as follows. It's basically this table here. This is the one that every school imprints on their science guide. But the rules are all nitrates are soluble. All acetates are soluble. Chloride, bromide, and iodide are soluble except for with silver, lead, and mercury. Sulfates are all soluble except for those with barium, lead, calcium, and strontium. Carbonates and phosphates are insoluble except those with sodium, potassium, ammonium. Hydroxide insoluble except for those with sodium, potassium, and hydroxide with barium, calcium are slightly soluble. Sulfides we don't really care about, and sodium, potassium, and ammonium, these are all soluble. Yes, you need to memorize this. Sorry. That's the truth. So you can make it easier for yourself. You can use acronyms. NAGSAG, PMS, Castro-Bear is a fan favorite over the years. So that basically just means always soluble substances are NAGSAG, nitrates, acetates, group 1, as well as sulfates, ammonium, and group 17. PMS and Castro-Bear tell you the exceptions. So PMS being lead, mercury, and silver. These are insoluble with sulfates and group 17s, so your halogens. And Castro-Bear is calcium, strontium, and barium. They are insoluble with your sulfates. This is one way to remember it. There is no one way. I didn't remember it this way. I crammed it every time in an exam before. So don't feel like you have to be in 2 days memorized. The way it's going to go is you're probably going to learn it for each exam, forget it, and then learn it again for the next exam. That's more likely what's going to happen. But the point is you need to know this for your exam. Don't care how you do it, you need it. There is a cheat method though, if you're really lazy, and it's this data sheet. Again, everything here on the data sheet, on these solubility constants, these are all insoluble. So if you're ever lost, you forgot your rules, you just don't know, you can always check against these constants to see whether things are soluble or not. Everything here is insoluble to some extent. But the numbers that are kind of a bit closer to 1, so -4, -6, -5, these ones are more likely to be slightly soluble. So you got to be wary of those ones, which are a bit on the, I guess, power lower side, but magnitude larger side. This is mod 5. So you're not expected to know these yet, but I'm just showing you that worst case scenario, you have somewhere to go to check where things are insoluble. Okay. So then to look at the cases, if you're mixing silver nitrate and sodium fluoride, if you do the double displacement and swap everything around, you'll make sodium nitrate and silver fluoride. Silver fluoride. So based on our solubility rules, fluorides are part of group 17, F, and the things that are insoluble with group 17 are PMS, which includes lead, mercury, and silver, and therefore silver bromide, or silver fluoride rather, would be insoluble. That's the way you have to go figuring it out from now on. You have a set of rules, and you can always figure out if something's soluble or not. Does that kind of make sense? Any questions so far? Another example. It's not a great variation. It's pretty much the same. Let's figure out one equation. Let's get familiar with these numbers. Copper sulfate reacts with sodium hydroxide. So you now have no longer any excuse to not write states. And these all start as solution. So they all should say solution after them. Copper sulfate solution reacts with sodium hydroxide solution.
Sorry, I had a question, but how do you know which thing to replace?
Good
Like
question.
you could do sodium and copper, so would that work, or is it like a specific thing?
It's always you're swapping both of the metals around, or you're swapping both of the non-metals around. Because you always need to match something positive with something negative.
Oh, I see.
Does that make sense for everyone? Okay, cool. I might just start going through just because we're a little bit short on time. But the one thing I wanted to test was, does everyone know what the 2 in Roman numerals means? How'd you describe it? What does the 2 mean?
That's a +2 charge.
As a +2 charge, so valency of +2. And that means that we're going to have copper sulfate, no number underneath. NaOH forms copper hydroxide and sodium sulfate. What's soluble here? What's insoluble here, I should ask? What's insoluble here? Is it sodium sulfate or copper hydroxide? Did anyone find it? Copper hydroxide or sodium sulfate? We can go back up. So copper hydroxide was the first one that we're trying to figure out. So looking at our rules, we go try and find where hydroxide is, and it doesn't fit into the NAG-SAG actually. So we'd go to our old solubility rules. So it's something that you build up over time. You realize that some things don't fit perfectly in all acronyms. So you might have to develop other rules as well. But hydroxides are insoluble except those of sodium and potassium. So therefore, this is going to be our precipitate. And the other, we can check as well, sodium sulfate. Sodium, group 1, always soluble, no matter what. So this is going to be aqueous. And that's where we go about that. So the states are solid and aqueous for the Na2SO4. Okay, so there's just one set of reactions left. Maybe I'll leave these till next time, just not to rush through them. But hopefully the framework is starting to become clear for these reactions going forward. You memorize a word equation that guides you as to what reactants and products you expect for that type of reaction, whether it's a displacement, whether it's a, what else have we done? Precipitation, and whether it's a synthesis, combustion, decomposition. As I said, synthesis, decomposition, a bit more general, but from combustion onwards, each of these should now be cases in your mind that you write out, you commit to memory, and you understand how it works. If you understand how it works, it'll be much easier to remember, but we'll leave it at that for today. Are there any final questions? Okay. Sorry for going a little bit over time, but I'll see you back next week. The homework this week is self-marked, so there's answers attached. Just trialing different methods for how we can do the homework. But yeah, no need to hand in homework this week. You have the answers attached. If you have any questions during the week, ask them on the Google Classroom, or you can shoot me a message as well. But I'll see you back next week.
Thank you. See ya.
No
Thank
worries.
you.
Thank you.
No worries.